In this lecture, I will be describing the real line. In fact, I will initiate the description of the real line. Then I will define what the modulus of a real number means, discuss a few properties, and also discuss what is meant by the extended real number system. So let us look at how to plot the rational numbers on a real line first. So draw a line on the plane and choose an arbitrary point on the line. Call that point to correspond to the number 0. So you have chosen an arbitrary point on the line, call it 0. Then you choose a certain length and take a line segment of that length on the line starting from 0 to the right of 0. So this line, the endpoint of this line segment, you call it 1. So we have chosen a unit of distance also. And then what you do is, if you take double the unit of this distance and plot the point, call that the number 2. And take triple of this unit distance and plot the point, call it the number 3, and so on, so that you will get all the positive integers plotted on the line along with 0. Now, using this unit distance, you can also plot the negative numbers. Conventionally, they are plotted on the left hand side of 0. So just take the same length as between these 2 points, which are depicted by 0 and 1 on the left hand side of 0, and the point which it describes, you say that it corresponds to -1. Double of that distance, you again plot the point and call the point to correspond to -2, and so on. So in this way, the set of integers can be plotted on the uh, straight line which you have chosen on the plane. Now, if you want to plot the fractions, what you have to do is a little bit of arithmetic and geometric calculations. So I'm just giving you two examples to see how this is done. First of all, suppose I take the fraction 2 by 7. So this fraction is between 0 and 1. So what you have to do is that look at this line segment which is uh, between the points corresponding to 0 and 1, and you partition it into 7 equal parts. Then you want the 2 parts out of 7 parts. So starting from 0, look at the first part and then the second part. The point which is at the end of the second part is the point which will correspond to 2 by 7. Similarly, if you have, say for example, the fraction -13 by 5, first you do the long division of 13 by 5. So what will you get? 5 2s are 10. So then you subtract 10 from 13, you'll get 3. So 13 by 5 is 2 3 by 5. That is 2 plus 3 by 5. So minus 13 by 5, it will be minus of, in the brackets, 2 plus 3 by 5. So what you will get is a number between -3 and -2. So how are you going to plot this number? You just see the denominator is 5. So you partition this line segment between the points corresponding to -3 and -2 in 5 equal parts. And then you take the point which is describing the end of the third part starting from -2, because it was -2 -3 by 5, right? So you have to take uh, partition three parts from -2 and look at the point which is describing the end of that three parts. That point will correspond to minus 13 by 5. So in this fashion, theoretically at least, you can plot all the rational numbers on the straight line. This straight line is called a real line for a certain reason, which will become clear as we go on. Okay, so now uh, we also know from the previous lecture that between any two rational numbers, there are infinitely many rational numbers. So you can imagine that the rational numbers are quite densely located on this real line. It came as a surprise that even though all the rational numbers are corresponding to the points on the line, there are certain points on the line which will not correspond to any rational number. So the simplest argument and very beautiful argument which was given is the following, that suppose you take a coordinate system on the plane and assume that the x-axis, so taking a coordinate system means that you have to choose a line which would be the x-axis, you have to choose a line which would be the y-axis, so you choose the origin also. So in the figure which you can see, I have not bothered to draw the y-axis, but the x-axis is going to correspond to the real line which we mentioned earlier. On this x-axis, now similarly you have plotted the points. Now instead of calling them 0, 1, 2, etc., since I am thinking of it as the x-axis, I am writing it as 0, 0, 1, 0, 2, 0, and so on. And now what I do is that from the point 1, 1 on the plane, I draw a perpendicular on this x-axis, and it will obviously have the foot of the perpendicular as the point A. So then you see that the length of AB is also 1. Length of OA is 1 and the length of AB is 1. Now what you do is you join the points O and B. So what you have constructed is a right angle triangle where angle OAB is the right angle. OA is your base and AB is perpendicular, OB is the hypotenuse. Now take a compass and place the point of the compass on the point O, and take this OB as radius and draw a circle. Then this circle is going to intersect the x-axis in 2 points. One will be on the right hand side of O and one will be on the left hand side of O. So for the time being, I am interested in the right hand side only, and where it intersects the x-axis, that point we denote as capital X in red. So let us just list out what all is happening here. The length OA and the length AB are equal to 1, and by Pythagoras theorem, the length OB squared is going to be length OA squared plus length AB squared. So that is going to be equal to 1 plus 1, which is equal to 2. Not only that, you have drawn a circle with the radius OB. So your length OB is going to be equal to length OX. So what can you deduce is that the square of the length OX is going to be equal to 2. What I want to claim is that this point will not correspond to any rational number. So what we do is you just assume that OB length is x. So then what are you saying is that OX will also be little x. So that x square should be equal to 2. This is what we want. So if we can get a solution of the equation x square equal to 2 in rationals, then that particular rational number will correspond to this point red x. So that is what we will show is not possible. So our theorem is that the equation x squared equal to 2 has no solution in the set of rational numbers. So what will we do is we will prove this by contradiction, which we have already discussed in the previous lecture. So suppose r by s is a rational number and suppose that its square is 2. So now what you can do is you can choose this rational number suitably. First of all, note that any such equation x square equal to 2, if it has a solution, then it will have two solutions. That is, if x square is equal to 2, then minus of x squared is also 2. So if I want to choose a rational number whose square is 2, I can first of all choose that this be a positive rational number. So there will have to exist a positive rational number whose squared is also 2. So let us start with that. And if that gives us a contradiction, then that means that we are assuming wrong. So first of all, you assume that r and s are both positive integers. Secondly, we know that any rational number can be expressed in its lowest form. So do that. That you, if there are common factors between r and s, then just cancel out those common factors so that the greatest common divisor between r and s is 1. So this you can do again without loss of generality. So you have started with a positive rational number whose numerator is a positive integer, denominator is a positive integer, and there are no common factors between r and s, so that r squared divided by s squared is equal to 2. Very good. So what does that mean? That means that r squared is equal to 2s squared. So that implies that r squared is an even number. That is, it is divisible by 2. So I claim that that means that r is divisible by 2. So there are at least two ways of seeing it. I have given one simple argument which is true, which can hold in this particular case, but which cannot be in generalized. But let us look at that. What we will do is, I want to say that if r squared is divisible by 2, then r is divisible by 2. So I will prove the contrapositive of this statement. That is, if r is not divisible by 2, then r squared is not divisible by 2. So if r is not divisible by 2 means it should be an odd integer. So it will look like something 2k plus 1, where you will be able to find some k so that r can be expressed like this. So if you take the square of that, you'll get 2k plus 1 whole squared. So that is 4k squared plus 4k plus 1. So which is again not divisible by 2. So what you have shown here is that if r is not divisible by 2, then r squared is also not divisible by 2. Hence, if r squared is divisible by 2, then r has to be divisible by 2. So this is proving a result by proving its contrapositive. Okay, so this is one way of seeing it. The other way is that you just take the prime factorization. I'm not very sure whether you know prime factorization at this particular stage, but at least you have done this in school, that if you were given any number, say suppose 136, then you could factor it out. That is, 136 will be equal to 2 into 68, and that will be equal to 2 into 2 into 34, and so on. So that type of factorization you can do. If you do the factorization of r in prime factors and the factorization of r squared in prime factors, then obviously what will happen is that the primes which occur in the factorization of r, their exponent will be just doubled when you are looking at the prime factorization of r squared. That is, if r is equal to p1 into p2 into etc pk, where P1, P2, Pk are primes, then R square is going to be just P1 squared, P2 squared, etc. Pk squared. So if there is no 2 in the P1 to Pk factorization of R, then there cannot be any 2 in the prime factorization of R squared. So that is also another way of looking at the proof of the same result. Okay, so what have we seen? That if R squared is divisible by 2, then R is also divisible by 2. So you can write R as 2 times something. So again I have written 2 times k, suppose. So just plug in this value in R squared is equal to 2s squared. What do you get? 4k squared is equal to 2s squared. So that means s squared is equal to 2k squared by cancelling out 2 on both sides, and therefore s squared is divisible by 2. But again that implies that s is divisible by 2. So however much you take the precautions of removing out all the common factors and so on, if you have that this result is true, then automatically both R and S will have to have the common factor 2. So there is a contradiction here. Therefore, what our assumption was that the R by S is such that R squared by S squared is equal to 2 is false, and hence the result that the equation x squared equal to 2 has no solution in the rational numbers is correct. So in the previous figure which we drew, this red capital X will not correspond to any rational number, this point. Now 2, instead of 2 you could have taken any prime number first of all and given a similar argument to show that x squared is equal to prime number has no solution in the set of rational numbers. So there are many points on the real line which will not correspond to these this type of equations. X squared is equal to, which are the solutions of this type of equations, x squared is equal to p, where p is prime, so they are also not rational numbers. Now instead of 2 you could have taken any other exponent, so say for example x cube or x to the power 4 or something equal to prime, so that also would not have any solution in rational numbers. So there are several equations which will have no solutions in rational numbers, infinitely many in fact. So there are many uh, points so called. If you agree to the belief that every point corresponding to this is going to correspond to a number, then there are several points on this line which will not correspond to rational numbers. So it will correspond to some numbers which are not rational. So those numbers included along with the rational numbers give a new number system. So let us just talk about it. So what I'm trying to say is that in fact there is a set R which contains Q and numbers which are not rational, on which the arithmetic operations and the order relation of Q are all extended. So you can extend the addition, subtraction, multiplication and division by non-zero numbers. Please note that on the set R, and also the order relation defined on Q can be extended to R. How do you extend this? Is not what I'm going to describe, but this extension will actually satisfy all the properties which were satisfied in the number system Q, that is all the arithmetic properties and all the order relation properties would be satisfied. So recall what was that: addition and multiplication were commutative, associative, and multiplication was distributive over addition. There is a special number 1, there is a special number 0, so that a plus 0 is equal to a for all numbers a into 1 is equal to a for all numbers a, and the order relation is transitive and it satisfies the trichotomy property, that is, given any two numbers you can compare them, they are one number is always either less than or equal to or greater than the other number, and there is this compatibility with addition and multiplication, that is, if a is less than b, then if you add any other number, then a plus c will be less than b plus c, and if you multiply with any positive number c, then AC will still be less than BC. So all these things will still be satisfied by R. In algebra, this whole paragraph can be expressed as R is an ordered field with Q as a subfield. So I am not going to prove this in this particular lecture, but this result was proved by many mathematicians were involved, but basically by Dedekind and Cantor. And they did it in two different ways, and surprisingly their results were published in the same year, that is 1872. What Dedekind did was he took subsets of the rational numbers, some certain types of subsets of rational numbers, called them the cuts, and then described how to add cuts, multiply cuts, compare cuts, and so on, and gave the whole description of the set of real numbers from there. What Cantor did was he looked at Cauchy sequences of rational numbers, and on this class he defined an equivalence relation. Then he looked at the collection of all equivalence classes of Cauchy sequences of rational numbers, and there he described what is meant by addition, multiplication, comparison, and that is the order relation, and so on, to get the set of real numbers. So these are quite deep results, and what we will do is that maybe at a later stage I will give a lecture on both of these ideas, but for the time being let us assume that there is such a set. I have not yet justified that there the existence of such a set means that that particular line which we had drawn in the beginning of this lecture can be called a real line. This set R is the set of real numbers. So the way I have tried to reach to this point is to try to justify that every point on the line will correspond to a real number, but that uh, we cannot settle that question, we cannot settle right now. We will take some time over it, but we will finally assure that that is actually true. Okay, so the next thing which I want to discuss is that suppose I have any real number x, then corresponding to that I can describe another real number which is called mod of x, denoted by mod of x like this, and it is called either the absolute value or modulus of x, or also mod x. So what is the definition of this function? That mod x is said to is equal to x if x is greater than equal to 0, and minus x if x is less than 0. So mod x will always be non-negative. Mod of 0 is 0, and say for example mod of 22 by 7 is 22 by 7, and mod of minus 15 by 61 is 15 by 61, and so on. Okay, for rational numbers at least. So if you draw the graph of this, you can just look at this function in two parts and then draw the graph. So look at the positive side. So again what I have done is I have chosen a coordinate system on the plane, which means that I have chosen one origin, chosen a line as the x-axis, chosen a line as the y-axis, This is the minimum requirement to draw the graph. So suppose I am drawing the graph of y is equal to mod x. Okay, so on the positive side, or rather the non-negative side of the uh, x-axis, what is the graph going to look like? It is just going to look like y is equal to x. So that is a straight line passing through the origin with slope 1. On the negative side of the x-axis, that is left hand side of the y-axis, the graph would correspond to y is equal to minus x. So that is again a straight line passing through the origin with slope tan 135 degrees, as you can see from here. So what you get is a V-shaped curve and which is having a sharp point at the origin. This is the graph of mod x, right? And one thing you just notice from here very easily, that if you take any positive number x, then modulus of minus x will be what? Minus x is now negative, so it will be negative of minus x, so it will be just x. So it is equal to mod x. Again, if you take a negative x, then modulus of minus x, now minus x has become positive, so modulus of minus x is going to be equal to minus x. And what is minus x? This is the modulus of x by definition. So what I'm trying to stress is that if you take any real number x, then mod x and mod of minus x are going to be equal. For 0, there is nothing to be said. Mod of 0 is 0. So this argument justifies this particular statement, that modulus of x is equal to modulus of minus x for any real number x. Okay, so we will prove certain inequalities now. The first one is called the fundamental inequality. What does it say? That if you take any non-negative real number, so k is greater than equal to 0, then for any real number x, the statement mod x less than or equal to k is equivalent to the statement minus k less than or equal to x less than or equal to k. So it is equivalent, can be also expressed as mod x less than or equal to k if and only if minus k less than or equal to x less than or equal to k. All right. So how will we prove this? Right now we don't have many tools in our armory. So what we will do is just we know the definition of mod x. So case by case we will have to prove this result. So first of all, assume that x is greater than equal to 0. Then what is mod x? Mod x is just x. So mod x less than equal to k, this statement is just the statement x less than or equal to k, this part. And this second part follows automatically because minus k is going to be less than equal to 0. K is greater than equal to 0. So minus k is going to be less than equal to 0 and x is greater than equal to 0. So you get this type of relation. So by transitivity, minus k is less than or equal to x. So this will automatically follow, and mod x is equal to x will imply that x is less than equal to k. So this whole thing will automatically follow from mod x less than equal to k, and also conversely. Similarly, if you take x less than 0, then mod x is equal to minus x. So the statement mod x less than equal to k is just the statement minus x less than equal to k. So if you just multiply this statement by minus 1, so that is this statement is equivalent to saying that minus k is less than equal to x. So this part minus k less than equal to x is just the statement. And also by staring at the inequalities, you notice that now x is less than 0 and k is greater than equal to 0. So again by your transitivity property, x is less than or equal to k. In fact, x is strictly less than k, but that is enclosed in the statement that x is less than or equal to k. So x mod x less than or equal to k is the same as the statement minus k less than or equal to x less than or equal to k. This is our fundamental inequality. Using So you can have another expression for this fundamental inequality, which I am not now going to uh, discuss. That is, if you take any two real numbers x and y, I have not bothered about writing k greater than equal to 0 here, but mod x minus y is always greater than equal to 0. So if I write such a thing, that means automatically k is greater than equal to 0. So for any two real numbers x and y, mod x and y, mod x minus y is less than or equal to k if and only if y minus k is less than equal to x is less than or equal to y plus k. So this is uh, very easy to prove using the previous inequality. Mod x minus y less than or equal to k is true if and only if minus k is less than or equal to x minus y is less than or equal to k by the fundamental inequality which you just saw just now. So now you add y to this whole inequality. What do you get? You get y minus k is less than or equal to x is less than or equal to y plus k. And these two are equivalent, of course. So you get this result. Mod x minus y actually expresses the distance between x and y on the real line. So therefore this is a very, very important quantity. And this is the algebraic part which is going to tell you that if the distance between x and y is less than or equal to k, then that means that x lies between the numbers y minus k and y plus k. So in some sense, it is giving you a relation between the geometric idea and the algebraic idea of numbers. Okay, so using this is the fundamental inequality, and the another inequality which is very important for our purpose is called the triangle inequality. What does this say? That if you have any two real numbers x and y, then mod of x plus y is less than or equal to mod x plus mod y. So just try to imagine that again why I call this a triangle inequality is that suppose from some point you go to another point a distance of mod x, imagine vectorially, and then from that point you go to some other point of distance mod y. This will take you a longer distance rather than if you started from the initial point and went to the final point straight away, covering a distance of mod x plus y, right? That since it comes from that triangle inequality, triangle path, it is called the triangle inequality, and it just says that mod x plus y is less than or equal to mod x plus mod y. So again, we will prove this by taking cases, several cases. So first of all, you assume that x and y are both non-negative. They have the same sign or both are 0. Okay. So if both are non-negative, then mod x is equal to x and mod y is equal to y, as well as x plus y also has to be non-zero. Non-negative. So mod of x plus y is going to be equal to x plus y, which is equal to mod x plus mod y. So if x and y are both non-negative, you actually get an equality. Similarly, if you take both to be negative, that x is less than 0 and y is less than 0, then mod x will be equal to minus x and mod y will be equal to minus y. Again, x being negative and y being negative, x plus y will also be negative. So, mod of x plus y will be equal to what? Minus of x plus y. So now you use the distributive law, you get this is equal to minus x plus minus y. So that is just mod x plus y. So if both of them are negative, even then you will get an equality. So last case is that when one is non-negative and the other is negative. So without any loss of generality, you assume that x is non-negative and y is negative. Then what is mod x plus mod y? First of all, we can easily write it down. This is going to be equal to x minus y. Now, what can you say about mod of x plus y? So that can have any sign. So we just take sub cases. First sub case is that when x plus y is non-negative. So if x plus y is non-negative, then mod of x plus y is equal to x plus y. So we have to show that mod of x plus y is less than or equal to mod x plus mod y. That is, we have to show that x plus y is less than or equal to x minus y. So you just add minus x on both sides. What do you have to show? That y is less than or equal to minus y. So again you add y on both sides. So you have to show that 2y is less than or equal to 0. But since y is less than 0, 2y is obviously less than 0. So that fact is incorporated in the fact that 2y is less than or equal to 0. So this is always true, and hence you have proved the result for this particular subcase. The only one now left out is that when x plus y is negative. So if x plus y is negative, then mod of x plus y is going to be equal to minus of x plus y. So that is minus x minus y. So again, to prove the result, we have to show that minus x minus y is less than or equal to x minus y. So what have I done? I added x plus y on both sides of this inequality. So I have to show that. So if you add x plus y on both sides, you'll get a 0 here and you'll get a 2x here. So if I want to show this is actually if and only if. So if I want to show this, it is enough if I can show this, that 2x is greater than equal to 0, but x is already chosen to be greater than equal to 0. So 2x is automatically greater than 0, which is, so therefore this is true, and hence your result is proved. So you have proved a very important result, that is, for any two real numbers x and y, mod x plus y is less than or equal to mod x plus mod y. Using this, we will also prove another result which is going to be very useful in our discussions later on. First of all, notice that if I take any two real numbers x and y, then I can write mod x as mod of x minus y plus y. So let x minus y be one number and y be another number. Then use triangle inequality. This becomes less than or equal to mod x minus y plus mod y. So just subtract mod y from both sides. What do you get? Mod x minus mod y is less than or equal to mod x minus y. So this is an interesting inequality which you get. There is nothing sacrosanct about taking x first and y later. So you can just interchange the roles of x and y. What do you get? You get mod y minus mod x is less than or equal to mod of y minus x. But we know that modulus of a number and its negative are the same. So therefore mod y minus x is equal to mod x minus y. So what are you getting? You are getting mod of y minus mod x is less than or equal to mod x minus y. So just multiply by minus 1. The inequality will change. What do you get? Minus of mod x minus y less than or equal to mod x minus mod y. So now look at this inequality and this inequality. Take them together. What do you get? Minus of mod x minus y is less than or equal to mod x minus mod y is less than or equal to mod x minus y. So if you call mod x minus y to be k and this to be some number, so say little a or something, what you are getting is minus k is less than or equal to a is less than or equal to k. So this is a familiar thing. What is this equivalent to? It is equivalent to mod a is less than or equal to k. That was your fundamental inequality. So just recall that mod x less than or equal to k is the same as the statement minus k less than or equal to x less than or equal to k. So in what we were doing just now was, instead of x I had mod x minus mod y, and instead of k I had mod x minus y. Let us go back. So that is our situation here. Minus of mod x minus y is less than or equal to mod x minus mod y is less than or equal to mod x minus y. So if you write it succinctly like this, you will get that is it is the same as mod of mod x minus mod y is less than or equal to mod x minus y. This inequality is going to be very useful to us later on also. So you have to stress on. So we have proved three basic inequalities using modulus of a real number. Okay. So the last thing in this lecture which I want to discuss is that what happens if we look at infinity and minus infinity, these two symbols. You will see while we are doing analysis, we are going to stress on the fact that infinity and minus infinity are only used to describe certain concepts. They are not going to have any, they are not numbers as such. This will be stressed many times. So the natural question which comes into the mind is why not? Why not use infinity and minus infinity also as numbers and do work there? So we try to do it here and call it the extended real number system. So suppose I take the set of real numbers and then I include two symbols here, infinity and minus infinity. So what do we want is, as we have been going on from the set of natural numbers to integers to rational numbers to real numbers, here again, so we have extended the number system in like this. So we would like all the arithmetic operations, order relation, everything to be extended here also, which will satisfy all the properties which we have already discussed. So what would be natural is what I have listed here, that we would like any real number to be greater than minus infinity and less than infinity. So automatically minus infinity should be less than infinity. Again, if you take any real number and add it to infinity, you should get infinity. If you add it to minus infinity, you should get minus infinity. If you take infinity and add it to infinity, you should get infinity. If you take minus infinity and add it to minus infinity, you should get minus infinity. So this particular statement and this particular statement is leaving out what will happen if infinity and minus infinity are added. So we will see that that is going to create some problems. Similarly, if I take a multiplication, then we know that multiplying by a negative number changes sign. So keeping that in mind, if x is a positive number and if you multiply it with infinity, you should get infinity. There is no problem. If you multiply a positive number with minus infinity, you will get in minus infinity. That will be a rule. But when you multiply infinity by a negative number, you should change the sign. So negative number times infinity will be minus infinity. Negative number times minus infinity will be infinity. And what will happen to infinity times infinity? It should follow this rule also. So it will be infinity. Makes sense. And similarly, minus infinity to multiplied with infinity will give you minus infinity. Okay. So this will satisfy all the arithmetic rules, commutativity, associativity, distributivity, etc. And I have just mentioned one uh, division formula, that x by infinity is equal to 0 and x by minus infinity is also 0 for any real number x except 0. We are missing it out here. Uh, no, I don't care about that. All right. So for any real number x, we take these formulas. Very good. So we have left out several things. We have left out what is the meaning of infinity plus minus infinity. And we have also left out here, you see, what is the meaning of 0 into infinity. So what turns out is that we actually cannot define these things. So we cannot define what is infinity plus minus infinity. So also the inverse of this, that is minus infinity plus infinity. We cannot define what is 0 into plus or minus infinity, and we can also not define infinity divided by plus or minus infinity. So these forms which cannot be defined, keeping consistency with the arithmetic rules and the order relation rules which had been described earlier, so these forms are called the indeterminate forms. Now, what I have tried to do is I have tried to give a justification as to why this cannot be done. So what I'm going to now talk of is not a proof of any kind. I will give you two reasonings as such why this cannot be done. We will not go into the details of the logic of why this cannot be done. First of all, let us see why 0 into infinity will lead to a contradiction. This requires a little bit analytical argument, but you have already seen limits of sequences in your high school, so there should be no problem in going through the argument. Let us see what is happening. We know that limit n tending to infinity 1 by n is equal to 0. We will discuss sequences in a later chapter in details, but at least you know these formulas from your high school. Again, if you take any positive real number and look at this sequence Rn, so that is going to look like what? R, 2R, 3R, 4R, etc. So that sequence is going to be divergent. So think of R as some number 2 or 3 or 4. Take them positive integers if you like. So this sequence is going to diverge, and we write it like this: limit n tending to infinity Rn is equal to infinity. Okay. Now what you do is you take a term by term multiplication of these two sequences. So Rn into 1 by n. You'll get a new sequence. And what are the terms of those sequences? They are all going to be equal to R, because n will cancel out here. So you get a constant sequence R. If you take the limit of that as n tends to infinity, you will get R. Very good. So it is making sense till now. Now there is a result in sequences which you have also seen in your high school, that this limit n tending to, if you take the product of the limits of two convergent sequences, it is equal to the limit of the product sequence. So now I want to include infinity as a number in the extended real number system. So I'm not going to say that this is divergent anymore. So in the extended real number system, this is also convergent. So this sequence is convergent and this sequence is convergent. So what should I get? I should get that limit n tending to infinity Rn into 1 by n is equal to limit n tending to infinity Rn times limit n tending to infinity 1 by n. So that means what? That R should be equal to 0 into infinity. But R is any arbitrary positive real number. So I am getting 0 into infinity equal to any positive real number. That is, 0 into infinity cannot be well defined, right? So I'm saying that 0 into infinity cannot be defined. So by this analytical argument, I try to give a justification of this. This is not proof of in any sense of the word. We have to go into some logic for that. We will not do that. Okay. As another example of some justification, look at this number. If it exists, infinity plus minus infinity. So if it exists, then it is going to be equal to infinity plus minus infinity. No problems, because infinity is equal to infinity plus infinity. That is already accepted. Similarly, minus infinity is equal to minus infinity plus minus infinity. That is also accepted. So using your arithmetic rules, by consistency, what should happen is that this one, infinity plus minus infinity, I should be able to write it as 2 times infinity plus minus 1 into infinity. There is no problem with that. And so this is equal to, by our distributive law, 2 plus minus 1 into infinity. All the laws should apply here. But 2 plus minus 1 is what? 1. So we get 1 into infinity. So I get just infinity. So this second expression is equal to infinity. What about the third expression? Infinity plus this in bracket minus infinity plus minus infinity. Again, this is going to be equal to minus 1 into minus infinity. No problems with that. Plus 2 into minus infinity. Again, use the distributive law. So it should be equal to minus 1 plus 2 into minus infinity. What is minus 1 plus 2? That is just 1. So it should be 1 into minus infinity. So it should be equal to minus infinity. So if this is defined, then this should be equal to these two numbers. But this number, if the arithmetic is consistent, has to be equal to infinity, and this has to be equal to minus infinity. So you are arriving at a contradiction because infinity and minus infinity are two different numbers. So there is no way we can define infinity plus minus infinity. So I hope that I have been able to give you some reasoning as to why certain forms in the extended real number system have to be left indeterminate. To tackle them, we have some other types of tools in mathematics, which we will discuss later. But because of this restriction on the extended real number system, in general, when we are doing real analysis, we deal only with the real number system, and infinity and minus infinity are treated as symbols, except in when there are some special cases where we will treat as infinity and minus infinity as numbers, but those are very rare. Okay. In the last lecture, I had talked about all the books which I have referred to and which I had suggested that you look at, except that I forgot to talk about Courant and Robbins's book, What is Mathematics? This book is not a textbook, but what it contains is the, first of all, it contains the idea as to how mathematics is done. That is how a certain proof came into the mind of mathematicians and so on. That is discussed to some detail, which is very useful for a student of mathematics to understand. And it also has anecdotes. It also has some extra topics related to the mathematics you will be doing in your undergraduate. So that also helps you to understand that why at all you are doing the type of things that you are doing. So in that sense, this book is useful to get a grasp on the knowledge of what you're doing as a mathematical student. So I would suggest that you also go through this book. So maybe I will stop here.